In this video, I'm going to go over section D, revision of factorization, which basically just means review of factoring. I'm going to make sure we finish the notes in this video that we might not have finished together in class. So first we start with the definition of what factorization is, or what factoring is, and it's the process of writing an expression as a product. So for example, if I had the number 72, if I can write that as a multiplication problem of something times something, that would be considered a factored version of 72. So I could write it, for example, as 8 times 9. Each of these would be called factors, and because we're writing it as a product, which means a multiplication problem, then I could consider this to be a factored version of 72. I wouldn't ask you to factor something as simple as just 72. We'll be introducing variables into our factoring. So something like x squared could be written as a product of something times something else. Of course, that would be x times x, so that would be the factored version of x squared. So normally you're given a problem like x times x and asked to simplify it to give x squared. Factoring is the opposite of that process. It gets a little bit more difficult if we have a couple of terms, 2 terms or 3 terms, where we're trying to write what is currently a subtraction problem as a multiplication problem. So in this case, I'm thinking of undistributing a number that must have been distributed into each of these terms. And if you're thinking, what can I divide both of those terms by? Because division is the opposite of distributing. I'm thinking I can divide them both by 2. And so there must have been a 2 that got distributed through a parentheses, and I have to figure out what's in the parentheses. So it's undistributing a 2 from the 2x, must have just been an x, and it's undistributing a 2 from the 4, so it must have just been a minus 2. And I want to check that indeed the left side and the right side of this equal sign are true. So if I were to distribute this 2 back in, you see how I would get 2x minus 4. So indeed that's correctly factored. Could make it a little bit more difficult by giving, let's say, a few more terms, maybe a 3x to the second power minus a 6x plus a 9. I'm looking at all 3 of these terms and thinking, what was distributed into a parentheses to give me this? Or what can I divide each of these terms by? And in this case, maybe you'll see they can each be divided by a 3. And so the first term must have originally just been x squared. The second term, if you're trying to figure out what must it have been, it's actually division that you're doing to figure that out. Because distributing would be multiplication. We're trying to undistribute, so we're dividing. So it would be a 2x. And then what would be left in the 9 when I divide it by the 3 would be a plus 3. So that would be factoring out the 3. So this number that we're factoring out, we still need to show it because I want the left side and the right side to be equal. I want somebody to be able to come along and look at my factored answer, which is this, and redistribute it to turn it back into what I started with. I don't want to just make the 3 disappear that I'm dividing out. The 3 that I'm dividing out is called the highest common factor that all of the terms had in common. Highest common factor. Now we're looking for the highest common factor. In each of the cases here, there's only been one factor that the numbers all had in common. So let's see what it would look like if we had more options and we wanted to pick the highest one. So perhaps we have a 4x squared minus an 8x plus a 12. And I'm looking at all these terms and thinking, I can divide them all by 2. And so that would look like factoring out a 2, and I'd have a 2x squared minus 4x and a plus 6, because I'd be dividing each of those by 2. But if you look at what's remaining in here, there's more that you could divide them all by. You could divide them all by 2 again. And so that means we didn't take out the highest common factor we could have to begin with. So we want to look back at it and find the highest number that all of the terms can be divided by. So in this case, that would be a 4. And then we're looking to divide that 4 out of each term. And we'd be left with this. So want to make sure that we're taking out the greatest or highest common factor that we can. Now in many of the cases, we're going to see that there's more than just a number we can take out. So for example, if I just had these 2 terms, not only can I divide them both by a 3, but I can also undistribute one of these x's from each term. So you can take out as many x's as all the terms have to give away. And since this term only has a single x to give away, I should only take a single x. out with the 3. So 3x is the greatest common factor from each term. And as I try to figure out what would be left, think about it again as division. So I'm taking my 9x squared and dividing by 3x. So there must have been a 3x in here. And I'm taking a 6x and dividing it by a 3x, which would just be 2. If you want to check your factoring, again, this is the factored version, so that's the final answer at this stage. That's what we're looking for. And if you wanted to check, you could always distribute back in and write down as proof for yourself that indeed the left side does equal the right side. So you've pulled out the greatest common factor. Let's get to some of the examples in our book. So the note at the top just says exactly what we've been doing. It's the reverse of distribution. Instructions here say to fully factorize. So I'm looking at, let's say in part A here, both terms and seeing not only can I divide them both by a 2, but I can also take an x out of each term. And that would leave us with a 3x in the first term and a plus 2 in the second term. And the second one is a little bit tricky. So we've got this group of a plus 1 that I'm actually going to be factoring out. You need to think about these groups as unbreakable. They have to travel as an entire group when they're in parentheses like this. And it's this plus sign that's actually separating the first term from the second term. So it's the entire bracket a plus 1 that the two terms have in common. So the bracket that I've underlined, like now in red, that entire bracket is what they have in common, each of the terms. So I'll be factoring out an a plus 1. What's going to be left from the first term, if I take out the a plus 1, what's going to be left is just the negative 4. And from the second term, when I take out the a plus 1, I'm going to be left with just the a plus 2 group. So this is a little bit trickier because it's factoring out an entire group from each of two terms. And then I might want to clean this up a little bit. I'll keep this a plus 1 out here. And in here, I really just have like terms, negative 4 plus a plus 2. So negative 2 plus a, or a minus 2. So to clean it up that extra step. There's a couple like that in our homework. And then this is something completely different. So the title here is important. We have difference of two squares factorization. I might move this down a little bit, do a few more examples up top before we get to those. So the note there that's in the blue box, a squared minus b squared equals a plus b times a minus b, makes it look exceedingly confusing. If we just see it with some numbers that are more familiar to us, you'll recognize what we're talking about here. So this result, x squared minus 49, this is the answer to a FOIL problem that might look familiar from having done x plus 7 times x minus 7. So we should recognize this factoring pattern where if we have two perfect squares, I'm going to underline in red what I'm talking about. These two numbers are perfect squares. They can both be square rooted. And there's a minus sign between them. That makes this a difference, and hence the title up at the top, the difference of two perfect squares, right? The difference of, and each of these are two perfect squares. This is x times x, and this is 7 times 7. So when I have the difference of two perfect squares, it's one of those FOIL problems where the first one was x plus 7 and the second one was x minus 7. To prove it to yourself that that does indeed FOIL correctly or distribute correctly, you can do first outer, inner, last, and confirm. We have an x squared minus 7x plus 7x minus 49. So because of those opposite signs, the middle two terms will cancel each other out, and you'll be left with the first perfect square and the last perfect square with subtraction between them. So the factored version of x squared minus 49 is x plus 7x minus 7, just like the example in the box at the top that has a's and b's in it. So it could get a little trickier, like if I gave us 4x squared minus 81. I'm checking to see that they are both perfect squares. I'm thinking, all right, what multiplies to give me 81? Yes, that's 9 times 9. What multiplies to give us 4x squared is a little trickier. The 4 we know is a 2 times 2, but how does 4 times 4, or 2 times 2 give us an x squared? Indeed, both 2's need to have an x next to it, because we need to have an identical thing. So 2x times 2x would be the perfect square that multiplies to give us 4x squared. So when I factor this, I'm looking at a 2x plus 9 in one of the parentheses and a 2x minus 9 in the other parentheses. So just recognizing we have perfect squares and then attempting to figure out what multiplied to give those perfect squares. So here's a few more examples. Here we recognize this is the perfect square 2 times 2. This is the perfect square 3y times 3y. So when I factor it, I'm just going to do 1 positive and 1 negative. You don't need to change the order at all. 2 plus 3y is fine. 2 minus 3y. You don't need to change it so that the variable comes first. In fact, you should not. And then b introduces a trick. So if you look at it right now, 9a, this is not a perfect square, because 3a times 3a would give us 9a squared, and that's not what we have here. And then you should recognize, I see what they've done. They've given us first a greatest or a highest common factor that I should be pulling out from both of these terms. So this is combining the first type of factoring from this lesson with the new type of factoring. So if I want to first take out a greatest common factor, there's nothing that 9 and 16 can both be divided by. So there's no number to take out, but I certainly can take out an a. And that'll leave me with a 9 in the first term and a minus 16a squared in the second term. But if I stop now, I haven't done this part of the instruction. I haven't fully factorized it because what's inside the parentheses can still go further. This is perfect squares, a difference of perfect squares, because I can see that 9 is 3 times 3, and 16a squared is 4a times 4a. So to go one step further and fully factor this, I need to keep this a that I factored out. Don't get rid of that. And then I need to break up this perfect square into 3 plus 4a and 3 minus 4a. And if someone were to come along and redistribute this final factored answer and simplify it, it would end up giving you exactly what you started with. So that should be enough examples to help get you through the homework. And that is all.